going to talk about linear functions. So, in terms of something being linear, if you notice in that word linear, you see that word line, but more goes with it other than just the word line. So, a linear function is a function whose graph is a non-vertical line. So if you see a picture of a graph and you want to know whether or not it is a linear function, it just has to be the shape of a non-vertical line. The other thing about linear functions is that they have a constant rate of change, which in the past you probably referred to that as a constant slope. And then one other kind of definition of a linear function is a function that can be represented by a linear equation. So if you took a look at this first set of points and you were to graph them, -4, -7, -2, -3, 0, 1, and 2, 5. You will see that when you look at all four of these points in a row, they appear to form a straight non-vertical line. So this is a linear function. If you look at your next set of points and you were to graph 0, 3, 1, 4, 2, 7, and 3, 12, you will notice that these points curve up and their line is not straight. So this would be nonlinear. If we take a look at some examples, it's pretty easy to see whenever you have a picture. So if you take a look at this first couple graphs, you will notice right away that this graph curves. So then this is nonlinear. On number 2, you will notice that it is a straight line. And anytime it's a non-vertical straight line, it is linear. If you take a look at number 3, we now have tables. In order for something to be linear on a table, you must have a constant increase or decrease on your x values and your y values. So if you take a look at your x values, what you will notice is that you are consistently adding 3. If you take a look at your y values, you will quickly see a pattern that you are subtracting 6. Because this is consistent and this is consistent, that makes it linear. If this was +3, +3, +3, and this was -6, -5, -4, then it would not be linear. So my next example, if you notice, you have a constant pattern where you are adding 1 here. But if you look here, you are subtracting 1, then adding 1, then adding 3. Because that is not a consistent pattern, this is non-linear. Whenever you get to equations, what you have to decide is whether or not can this equation be represented by a linear equation. You guys are used to seeing linear equations written in slope-intercept form. So what you have to decide, is there a way I can get this equation in slope-intercept form? Another kind of easy way to tell is that in order for it to be linear, it typically has an x and a y. It does not have to have an x, it could just have a y equals. But it can't do crazy things on the x. There can't be any square roots on the x can't be squared or cubed, the x cannot be on the bottom. So if there's any crazy things happening with your x, it would not be linear. So if you take a look at this, this can easily be written in slope-intercept form, and that would make it linear. And if you notice, the x and the y are pretty straightforward. Whereas this case, if you look at the x, it's being cubed. So anytime it is being cubed or squared or square rooted, it is nonlinear. In this next problem, if you recall, y equals, without an x, is a horizontal line. So this would look something like y equals 10. It would be a horizontal line crossing your y-axis at 10. Because this is a horizontal line and not a vertical one, it is linear. Next one, if you were to distribute the 6, you would get 6x minus 6, just like a nice, beautiful line in slope-intercept form. So he is also linear. Number 9, because of that square root, he is nonlinear. Number 10, because of that x squared, he is nonlinear. Number 11, because that x is a power, he is also nonlinear. And then you have number 12. If you were to distribute number 12, you can quickly see that you can get it in a nice slope-intercept form for a line, so he is linear. So the next thing we're going to talk about is whether something is discrete or continuous. So when we look at graphs, you're going to look at these things called discrete domains and continuous domains. So a discrete domain is the set of input values that consist only of certain numbers. So for example, if you notice, these are all dots. The domain here would be 1, 2, 3, 4, and 5. So you would write that as a list. Whereas in this case, this is a continuous domain. It is all the numbers from 1 to 5. And that would be written as an inequality. So discrete, a lot of times people think of discrete as dotted and continuous as connected. But if it's discrete, it will be a list, and if it's continuous, it will be an inequality. So on my first example, you will notice that this is a connected line, so that means that this graph will be continuous. On my second graph, it is a bunch of dots that are not connected because it's dotted. This will be discrete. So if we take a look at our first example, they give us this linear equation where y is your cost and x is your number of tickets. So this equation right here, y equals 15.95x. It says each customer can buy a maximum of 4 tickets. So if you notice, they give you that you can buy a max of 4 tickets. And because tickets deals with my x, that means that we are going to start by looking at this domain. So if I can buy a max of 4 tickets, that means 4 tickets can be my most. I could not go at all and buy no tickets, but then you have to decide how to write this domain, whether it will be discrete or continuous. So the way I like to look at it is I try and figure out whether or not I could have a partial ticket. So because I'm talking about tickets for my domain, could I buy 1.8 tickets? Because the answer is no, then I list my points for my domain. I could buy 1 ticket, 2, 3, 4, or I could not buy any at all. Once I figure that out, I can then say that the domain is either discrete or continuous. Because it is a list, this domain will be discrete, and the reason would be is because you can't buy a partial ticket. You either buy a ticket or you don't. Let's try another one of those. This time we're talking about a cereal bar. So every cereal bar contains 130 calories. The number C of calories consumed is a function of the number of bars eaten. So the first thing I'm going to do is I'm going to try and figure out an equation for this. So each bar equals 130 calories. So depending on how many bars I eat, and maybe I should kind of flip this around here, the number of calories I'm going to partake in or eat is going to be 130 times the number of bars I have. So in this case, that is my equation. So the first question they ask is this a linear function? If you think about this as my y and this as my x, you can clearly see that it is a linear function. Another way to look at that is it does have a constant rate of change, because for every bar you eat, you have increased 130 calories. The next part is find the domain. So in this case, the domain deals with my x's, which in this case is my number of bars. So I think about how many bars I could eat. Could I eat 1 bar? Yep. Could I eat no bars? Sure. Could I eat 22 bars? Sure. I could really eat 22 million bars. Maybe not realistically, but mathematically you kind of could. The question is, can I eat a partial bar? Could I eat 2.7 bars? Because I could eat a half a bar, my domain will be anything greater than or equal to 0, because I could eat no bars, but I could also eat up to infinity for the number of bars. Because I could eat a half a bar, then my domain is going to be continuous. Because I can eat a partial bar. My last example says a 200-gallon bathtub is draining at a rate of 2.5 gallons per minute. The number G of gallons remaining is a function of the number of M minutes. So the number of gallons I have left. Well, I know that I start with 20 gallons. Because I am draining, that means I am losing 2.5 gallons per minute. So if you take a look at that equation, you will quickly see if this was y and this was x, that it would represent a linear function. It's just like an equation with y and x in slope-intercept form, and it has a constant rate of change. The next thing you look at is the domain. So the domain deals with my x or my m. My m is the number of minutes. So in this case, I could drain it for no minutes. The water could just sit in the bathtub. But because there's only 20 gallons in the bathtub, that means it couldn't drain forever. So we have to figure out how we'd come up with the final number of minutes where the water would no longer be located in the bathtub. So if I want 0 gallons left in my bathtub, I can plug in 0 for G and solve that for M. So if I bring the negative 2.5 to the other side and make it positive, I can then divide by 2.5, and it's only going to take 8 minutes to get that 20-gallon bathtub completely empty. So I know my end game, or my end number, is 8. The question is that can you have a half a minute? Because you can drain it for 4.2 minutes. We know that this is not going to be a list, but instead it's going to be an inequality. Once you see that this is an inequality, you then know that your domain is going to be continuous.